All right, so we already talked about the electromagnetic spectrum, but I wanted to get in a little more detail with, in terms of spectra with you folks. Now, this should be relatively familiar with you. I kind of like my creative little way of illustrating the basic electromagnetic spectrum. Here's that little thin film of light we were able to be sensitive to with our eyes, which is visible. But there's a whole wide world out there that's beyond our capability of detecting it without using other means. We're going to spend a lot of time this coming school year in radio waves. I mean, a little bit of microwaves. Sometimes there's what we call some X-band radio emissions that kind of border on kind of the gray area between radio and microwave. Then there's infrared, which you feel is heat. Ultraviolet, which is where your skin cancer comes from. X-rays, of course, which are used to see the inside of your body in various ways, and then gamma rays, which these two they're really high energy, very very high frequency, and very very short wavelengths. So they tend to be very kind of dangerous. So the longer the wavelength, you already discovered, the redder the light. The shorter the wavelength, the bluer the light. Likewise, stars that are blue have light that's emitted at very high frequencies. The maximum intensity of light are emitted at very high frequencies, and stars that are red have light that's emitted at lower frequencies and is cooler in temperature. So to sum up your lab from last Friday, that's what I would probably say. But of course, you all know that white light, when passed through a prism, will yield you a continuous spectrum. Continuous because you can see everything from the low frequency red, short wavelength red, long wavelength red, all the way to the short wavelength violet, and so forth. So without any breaks. But in reality, there's other kinds of spectra that are called emission spectra. When you excite or heat, when you excite an atom, such as heating it, it will emit. It'll emit certain frequencies of light, like these frequency bands here, okay, that are a signature for that particular form of light. So what we see here, the top one you saw right here is an absorption spectrum. So that's a continuous spectrum where light is passing through a gas, and we're on the other side of that gas, and that gas that it passes through absorbs certain wavelengths, and we end up with this continuous spectrum. But we can still tell, what's in that gas the light passes through by which wavelengths of light are missing, and in this case, hydrogen gas. And then, of course, there are emission spectra, where a hydrogen atom actually emits a photon of light due to being heated or whatever, because the electron actually moves down in energy level when this happens. So, what do they mean? Well, these are signatures. Every atom has a specific emission and absorption. An emission and absorption spectra are exactly opposite of each other, but every atom has a signature in this regard. So we can detect exactly what elements are in stars based on that signature. It's pretty cool. So that was just invisible light, right? So but can you get these spectra at other wavelengths of light, like radio or gamma and so forth? Well, sure you can. It's just easier to, it's been easy to talk about it in terms of visible because that's what our eyes are sensitive to. But if we're going to look at it in other wavelengths, then, well, that's of course answering the question, yes. Then it's going to look more like this. And instead of actually looking at necessarily the Balmer lines, which are the emission lines you see in the visible light spectrum, you'd be looking at either the other sets of lines, Fraunhofer and so forth, that you learned about briefly in the lab. I'm not that concerned that you understand the difference between the different types of lines, but just to know that if we look at wavelengths, these are wavelengths of 4,000 to 8,000 nanometers, and at those wavelengths, this particular star, these are supernovae, which of course are explosions of stars. Type 1 are huge explosions of stars, type 1a specifically, but they have a lot of silicon, and silicon is a heavy element that doesn't get produced in a star unless you have a really massive supergiant star. And you can see the silicon line, and this is in this case when it's when you see the line go down like this, that's an absorption spectrum. So you're seeing silicon is in the gas within that supernova because the light from that supernova is passing through silicon gas. That's kind of a weird thing to think of, silicon gas. and the silicon's absorbing it. So we see at certain wavelengths dips that are where the silicon atoms are absorbing photons of light from that supernova. Likewise, we see helium as well and oxygen. This is a different type of supernova. There are several different types of supernovae, in case you didn't know that. This one is these types of supernovae only really occur with white dwarf stars, so they're not nearly as powerful, and they only show emission. There's this really prominent emission line. So when a peak goes up like this, that is good evidence of emission. This would be another emission line over here. When you get a big dip, that is absorption. So in this case, we have a major H alpha emission line, and here's a major H beta emission line. H beta is not as powerful. But that's the idea. So peaks are emissions and dips are absorptions out of the wavelengths. So that's kind of summarizing it. All right. So stars, we're looking invisible again here, but back at this, stars can have a lot of elements in them. So they generally do. Even our sun has a lot of elements in it. And if you look at the spectra of one major star, you might get the continuous spectra, just like the solar spectrum here, and they've highlighted some absorption lines. But then these are the emission spectra. This is a basic absorption spectra. And then these are the emission spectra of various elements. So there's potassium, rubidium, cesium, and so forth. So there's a fair number of large elements within the sun. Though, of course, those elements aren't being produced by the sun yet. They are relics of the nebula in which our sun formed that did have those larger elements from previous stars that had gone supernova. But those elements, nonetheless, do exist in the sun. And we can detect them by looking at the emission spectra. And sometimes, like for instance, the sodium has emission lines at many more places than just this one yellow wavelength. But we're not seeing them all. We're only seeing a single sodium line. So, you don't necessarily see, you're not able to necessarily distinguish the complete signature all the time. All right, so certain elements emit and absorb at certain wavelengths. All right? The emission and absorption are exactly opposite. So yes, every element emits at certain wavelengths as well as is absorbed at certain wavelengths, or absorbs light at certain wavelengths. So therefore, we can use the light anywhere from radio to gamma to tell us what an object in space is made of. And here's another example, of course. We're looking at a supernova. This is I believe this is Tycho's supernova. But these are all different elements that can be found in that supernova, and they have them pointed out for you. And these are, this is Tycho's supernova. These are a couple other supernovas, just for comparison. So the nice thing is here that, when it comes to certain types of supernovas, this is a type 1A supernova comparison. Type 1As we kind of think of our lighthouses, and they're a basic supernova that we know always looks the same. And here's a good example of how they always look the same absorption lines, same emission wavelengths, and so forth. All right, so that's the main take-home message. We're going to be looking at a lot of spectra, or a number of spectra in the coming weeks that look like this. With the wavelengths down here and the flux over here, which is really just brightness. Okay, but so absorption lines, again, are going to be dips, and emission lines are indicated as peaks in these graphs. So in the case of radio, it's the same deal. All right, so by the time you've watched this, you've probably already done the Spectrum Lab, but that's okay. This is an important topic for us to start off the second half of the 9 weeks with. Let's have some fun with it.